This is How to Math with Dr. Ian Lundholm. In today's episode, comparison tests. All right, there are two major tests that we're going to talk about today. The first is just the direct comparison test, where we will directly compare two series based on their terms and say whether series converge or diverge. The next one is a little bit more subtle. The limit comparison test, we'll be looking at the ratio of limits of successive terms of two different sequences or two different series, comparing those along the way to make judgments, again, about convergence or divergence. So here are the four cases that I'd like to look at first. We have two series. The first is smaller than the second. So here we have AN is less than BN for all N. So if we have the bigger series converging, what does that mean about the smaller series? It would converge as well. If the big series converges, the smaller one should converge as well. I guess I didn't point this out earlier, but we are working with terms in our series that are all positive. So yes, if we're working with the bigger series and that converges, then the smaller one does too. Case number two, if the big series diverges, can we say anything about the smaller series? No, that one just gets an extra question mark. If the big series diverges and the smaller series, we don't necessarily know anything about the smaller series. It could converge. It's smaller. Or it could diverge. Doesn't know. We don't know. Number three, if the small series converges, what can we say about the big series? Well, in that case, again, the small series converges. We don't really know whether the big series converges or diverges. It's bigger. That's really all we know. But if we get down here and we know that the smaller series diverges, can we say that the bigger series diverges as well? Yes. So yeah, two of those cases were actually relevant, and that forms the basis of the direct comparison test. So just in summary, if you have, if you have a big series that converges, the Bn is the big one. If that one converges, then the small one does too. If you have a small series that diverges, the bigger one, then that small series diverges as well. Those are the two big cases. And here, oh geez, that's not what I wanted. Good grief. All right. There's a small proof here talking about part A. We can say that AN converges due to the bounded monotonic sequence theorem, looking at the partial sums and stuff. And this one, this is the divergence part. It's not a huge deal. Let's take a look at some examples. Use the direct comparison test to determine whether each of the following series converges or diverges. So the name of the game here is these series are a little bit unfamiliar, and what we'd like to do is compare them to a series that we know better. And if we have a hunch that this series is going to converge, then we should pick a convergent series that is bigger than the one that we see here. Whereas if we have a hunch that this series that we see will diverge, we should try to pick a smaller series that diverges to prove that this one will diverge as well. So we need to come up with some more common familiar series. This first one, part A, kind of looks a lot like the harmonic series 1 over n, right? At least in terms of the powers of everything involved here. Kind of looks like 1 over n. And so maybe that one diverges. That's a hunch. This one, part B, with the factorial in the bottom, a factorial is a product, right? It's a bunch of multiplication. And so those fractions are going to look much smaller than the harmonic series. I would guess that this one would converge. And then looking at the last one, it's fairly similar to 1 over n as well. We'll have to see. Here we go. Let's take a look at solution for part A. Yeah, rational expression, those are similar. We've already said that. Yeah, what we really need to check is just to see if the terms in this series actually are larger than the harmonic series. And it doesn't necessarily have to be for every single term, but we do need, for the direct comparison test, we need this series to be bigger than the harmonic series for all n past some number. So this happens to be true for n greater than or equal to 2. Yeah, and there's, the algebra behind it up at the top of the screen. But yeah, since the harmonic series diverges and its terms are less than the terms in that, this new series diverges as well. Cool. Moving on to the factorial one. So this is what it looks like to have, the factorial going on. And what we're going to do is compare this factorial to a geometric series. You can see here that, we can make comparisons between these and these. These are equal. The less than sign applies here because 1/6 is smaller than 1/4. Similarly here, 2 times 3 times 4 is 24, and 2 times 2 times 2 is 8. So the top one is less than the bottom one here. And so we have this less than comparison this entire time. And so if we can show that the geometric series converges, then this factorial series is going to converge as well. And yes, the geometric series converges, so the factorial series converges as well. Cool. All right, now let's take a look at this weird one. The ln of n over n is somewhat similar to 1 over n. We might start comparing it to the harmonic series. And since those terms are non-negative and larger than the harmonic series, it diverges as well. I guess that one was relatively straightforward. Cool. It says you could also use the integral test too for that one. Yeah. Okay, that makes sense. Moving on. Okay, here's a question that's not necessarily in our book, but I wanted to ask. Which comparison would be more useful? Just to start developing our eye for these kind of things, like making comparisons. Would it be more useful to compare it to this geometric series or the harmonic series? Over time, if you let n go up to 10, say, This one would look like 1 over 2 to the 10th plus 10. And the 2 to the 10th part is much, much, much bigger. I mean, 2 to the 10th is 1024. So this fraction looks a lot more like the geometric series. And so that's just an example of something to look out for when you're trying to make comparisons that are more useful. Maybe think about what happens 10 different 10 terms down the line, and yeah, which one seems to be more similar. Here's another question that is not necessarily in our text, but I think is interesting to think about. Show that if we have a convergent series here with an, we don't really know the properties of an other than an's always going to be non-negative. Show that if that series converges, then the similar series, except the an terms are squared, also converges. Now, this one could initially be confusing because, starting off with positive numbers like, 10, if 10 was one of your sequence terms and you ended up squaring that, you would get 100. And that, would seem like a bad thing, right? Like, you wouldn't want the series to get larger, then it's less likely to converge, right? But the big idea here is that at some point, since an has to approach 0 as n goes to infinity, we know that because it's a convergent sequence, right? The series terms have to go to 0 in order for the series to converge. There will be at some point, there will be a big N, where a sub big N and a sub big N plus 1 and so on and so forth, all of those terms will be less than 1. So this gets to like the idea of, having a limit that approaches 0. 1 is our epsilon here, if you want to look at that, definition of the limit. But yeah, there will be, at some point n, everything else will be less than 1. And what's really important is that tail exists. It's always the tail end behavior of the series that determines the overall behavior. So yeah, if we have, some number of numbers up here, we're starting off with a1, a2, a3, we go along, we get to our big a sub n, a sub big N, and then a big N plus 1, and then on and on and on. It is fine if these first so many terms, big N minus 1 terms, are large. They could be numbers like 100, 1,000, whatever. The big idea is that there are a finite number of these terms, but the tail end, even though these numbers might be, relatively small in size when you look term by term, there are an infinite number of these terms. And since we have an infinite number of these terms that are less than 1, when you square a number that's less than 1, say, like 1/2, when you square that, you get 1/4, and you get a number that's smaller. So we have this result that the new series with all the terms squared converges by the fact that we can use the direct, we can use the direct comparison test because the tail end of this series is all going to be smaller than the original series, AN. So I think that's really cool. Moving on. Limit comparison test. Now this is, a little bit more powerful, a little bit more subtle than the direct comparison test. Here we get to look at series that are maybe even a little bit weirder. We're looking at this series where we've got 2 over 3 to the n minus 7. It does seem very overall similar to the geometric series 1 over 3 to the n. But the rub here is that it doesn't interface nicely, being nicely less than 1 over 3 to the n for a bunch of, for all of its terms. And so while we have a hunch that it might be convergent, 1 over 3 to the n is not a perfect comparison to it, at least by the direct comparison test. What we're going to see is that if we use the limit comparison test, though, that this geometric series can be a very good, useful thing. Right. And so, the terms of the new series are larger than 1 over 3 to the n. Boom. Here are the 3 major cases of the limit comparison test, and we're going to look back at the result of this one soon after looking at this. But the limit comparison test, again, it's a comparison test where you're looking between 2 different series, and you're starting off with a series that is unfamiliar, and you're creating a new series that is familiar that you think would share this, a very similar limit over time. So if the ratio between the terms in those series ends up approaching some constant number, then both of the series either converge or both diverge. They go together. What that's saying is that eventually, if the limit of that ratio approaches some constant number, it means that the 2 series that you're working with are very similar in their tail end behavior. And so they go together. For part B, here we're working with that same ratio, but in part B, Bn is bigger, and let's say, it's quite a bit bigger than An in limiting behavior, so we're still looking at the tail end of it. But by the tail end, Bn is much bigger than An, and so that ratio tends to 0, like a something over infinity kind of thing. And this is making use of the same kind of logic as in the direct comparison test. If the bigger series, Bn, converges, then the smaller series, An, converges as well. So, Bn is the more familiar series. So here, if your familiar series converges, then your unfamiliar series converges as well. And on the bottom one, An is much bigger than Bn. And if the small series diverges, then the bigger series diverges as well. And so there's, very fundamental reasoning similar to the direct comparison test. But here we are looking at the limits, the limit of the ratio between 2 different series. Yeah, let's take a look at some examples. What? Oh no. I'm stuck. Come on. All right. Sweet. I know that this isn't the end. Let's discard those ink annotations. Good grief. All right, let's get back into this. Example time. Here we go. Sorry, guys. The limit comparison test can be used on this series. Again, it's very similar to the geometric series 1 over 3 to the n. And so what we do is set up a ratio between these terms. This is an on the top over bn on the bottom. Oh, and this is going to, oh, great. And when you reduce some stuff there, you end up finding out that the limit is 2. Yeah, and that's just some algebra. I mean, I suppose you could use L'Hopital's rule and stuff like that. But fundamentally, we're coming out to a constant number here, which means that the new the unfamiliar series and the familiar series both converge or diverge together. And therefore, this unfamiliar series converges, just like the geometric series. Cool. Example 3, we get to take a look at 3 more, and we get to use the limit comparison test. I think it would benefit us to think about what kind of comparisons, what kind of more familiar series do you think would be good comparisons with the ones that are given? And I would encourage you to take a moment and think about that. I guess if you're watching live, I'm not going to wait too long. So yeah, that first one, it kind of reminds me of 1 over n squared. I guess we have to be kind of careful about what happens on the top there, the square root, or like the nth root of n. But taking nth roots, I feel like is going to catch up. I think that top part's going to be pretty small. So I might start with 1 over n squared on part A. For part B, the largest degree on top is 2. The largest degree on bottom is 5/2. And so I bet this thing would behave a lot like square root of n? No, 1 over the square root of n. Shoot. Yeah, it would behave a lot like 1 over square root of n, because we've got 4 halves on top, 5 halves on bottom. Okay. And let's think, the next one, we've got 1 over the square root of n times ln of n. So part of me thinks, if you look at the square root of n, that part kind of looks like a p series with, p equaling 1/2. But you've also got this ln of n part, and you've got the product between them. So that's going to get bigger. If it was just the p series, that thing would diverge. But it's kind of hard to say when multiplying times the ln of n. You also got to think about the harmonic series in relationship to this. I guess if anything can be learned from the rambling that I just did, is that there's not necessarily one right way to do this. You have to kind of use a little bit of intuition about what the behavior of these terms will be as n goes on. And sometimes you'll make comparisons that are helpful, and sometimes they won't be helpful, and you'll have to try something else. But let's go ahead and let's look through these solutions real quick. So the first one, we've got the nth root of n over n squared. And here we pick 1 over n squared for our more familiar sequence. The direct comparison would be inconclusive. But if we worked with the square root of n, the nth root of n, that would approach 1 as n approaches infinity. I guess that was done not too long ago, but I don't know. Yeah, that would look like n to the 1 over n power, and we're looking at the limit as n goes to infinity. In order to figure this one out, I think you have to do some stuff with logarithms. I think you have to do the e to the ln part and have n to the 1 over n power up there. Yeah, it gets a little bit ugly. It does end up just being 1, though. E to the 1 over n times ln of n. And then you can do L'Hopital's rule on this part. You've got ln of n over n. You could do L'Hopital's rule. You see that this part approaches 0, and then the overall one would approach 1. Well, e to the 0 is 1. Okay. All that is to say, we can use the limit comparison test here with 1 over n squared. We get this limit, and that limit eventually approaches 1. Cool. So, since 1 over n squared is a convergent p-series, then our new series is convergent too by the limit comparison test. Because they both convert, like the ratio of their terms approaches a constant number. That's why they go together. Here, yes, these do tend to look similar to this or similar to this. That's even simpler. So yeah, 1 over n to the 1/2 is a reasonable series to test against. Here we do the limit comparison test. And this is a little bit ugly. We end up multiplying by n to the 1/2 power on top. And then to really evaluate this limit, we end up dividing by n to the 5/2 everywhere. So that we see that this approaches 1 in the end. And so we again have the situation where these should converge or diverge together. And they're going to both diverge together because this guy's a divergent p-series. Cool. The last one. We have a product of square root of n and ln of n. We're going to take a comparison with the harmonic series. When you compare that, some powers of n cancel there. We use L'Hopital's rule and end up getting a limit comparison number here that goes to infinity. So how do we interpret that? That means, okay, the ratio of these two things eventually tended towards infinity, after doing L'Hopital's rule and all that stuff, which means that the top series is bigger than the bottom, smaller. Now, the harmonic series is not small. We know that that diverges. And since the top part is bigger, that one diverges as well. To give you a little bit of intuition on, why that works, if we had 1 over the square root of n times the square root of n, that would exactly be the harmonic series, right? But what we've done is we've replaced one of these square roots of n with ln of n. And ln of n actually grows even slower than the square root of n. And so this series, this product is going to be somewhere in between this divergent p series and the harmonic series. So yeah, it diverges. Ln of n is going to be a really small number. Again, if you think about, say 100 terms down the line, this one would be 1 over the square root of 100, or 1 over 10. This one would be 1 over 100. And this one would be somewhere in between. I think I did this earlier. Yeah, if you look at 100, the ln of 100 is only 4.6. So, yeah, you'd have 10 times 4.6 there on bottom. But yeah, it diverges as well. We're between two divergent series there. Okay, and that's it for section 10.4 about comparison tests. So this has been How to Math. And I want to remind you that you have online homework to do, and now you're ready for it. All right, I'll see you guys on Pronto. Have a good one. Bye.